Good afternoon and welcome to the American Floral Endowment Grow Pro webinar series. I'm your moderator, Melissa Muñoz. I'm a member of the AFE's Young Professional Council and an NC State University postdoctoral research scholar at the Mountain Horticultural Crops Research and Extension Center. I have a master's and a PhD in plant and environmental sciences from Clemson University, both working with botrytis blight management in cut flowers. Today's session is on hydroponics for floriculture production. On behalf of the Endowment, I'm excited to be part of the AFE Grow Pro webinar series that features a new topic every month, presented by an industry expert. The webinars are free to everyone thanks to the generous support of the AFE sponsors. If you would like to learn more about sponsorship opportunities, you can find that information and more about the webinar series on AFE's website at endowment.org/growpro that you will find in the chat. Today's session will be presented by Dr. Chris Currey. After the presentation, we will open up the discussion for questions. So feel free to submit your questions through the Q&A feature or the chat at any time during the presentation. We will answer as many questions as we can before the end of the hour. Unanswered questions may be answered through a separate email exchange. This session is being recorded and will be shared through the AFE's YouTube account. Through YouTube's accessibility features, you can access closed caption in other languages. To get us started, I would like to share a bit about today's expert speaker. Dr. Chris Currey is an assistant professor at Iowa State University. His control environment and greenhouse crop research is focused on providing research-based best management practices to support commercial producers of ornamental and food crops to improve productivity, profitability, and sustainability using and managing light, temperature, mineral nutrition, and plant growth regulators. In his scholarship of teaching and learning, his goal is to identify specific methods to increase student confidence and success in greenhouse crop production and increase student understanding of timely and important related greenhouse crop production, such as local food security and native plant production. Dr. Currey, welcome and thank you for presenting today on hydroponics for floriculture production.
All right, well, thank you very much for that introduction, Melissa. And again, today we are going to be looking at hydroponics and floriculture with a specific reference to cut flower production, because that's really where we see the most hydroponic system used for floriculture crop production. Now, first, before we get into hydroponic system and controlled environments, I want us to think a little bit about the 5 different factors of plant growth and how they affect plants and why we need them to produce plants. So first one is going to be light. For obvious reasons, plants photosynthesize, so they need to have light to convert that into sugars inside their through biochemical processes. Plants also are going to need air temperatures that are adequate for growing. They can't be too hot or too warm, nor can they be too cool. Plants also need different gases. Specifically, they need oxygen and CO2. Carbon dioxide, CO2, is going to be most important for the shoots of the plants, where their foliage is, because again, those are where the stomata are, and that's where that carbon is going to be taken up for photosynthesis. But oxygen is also going to be important for the whole plant, but in some hydroponic systems specifically, as you'll see later, it's important for the root systems because roots respire and they require oxygen. Plants also need water, as we all know, because that's going to be their lifeblood and help keep their biochemical processes functioning. And they also need mineral nutrients in adequate amounts to function and complete their life cycle. Now, we can't talk about hydroponics without talking about controlled environment agriculture. You hear CEA all over the news these days. And really, what controlled environment agriculture is any agricultural technology that enables the growers to manipulate a crop's environment. And this is usually done to try and get those desired conditions that will optimize or maximize the production of our floricultural crops. Now, hydroponics in controlled environments are not mutually inclusive. You can have hydroponic system out of doors. This is actually quite commonly done in Australia for food crop production. And you can also have crops grown in field soils inside of a greenhouse. And you'll see an example of that later in this presentation. However, very, 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 very frequently, we're going to see controlled environments and hydroponics used together to produce crops. So to understand where we are today with controlled environments, I want to talk a little bit about how we got to the places that we're at now, because really that helped develop our hydroponic systems as well. So I'm going to take you through a little bit of a development in controlled environments over time. So the first controlled environment that we ever had was the Specularibus. And the Specularibus is something that was used to produce cucumbers for a Roman emperor, the Emperor Tiberius. He wanted a cucumber on his plate every single day of the year, and that was only possible by modifying plant culture to grow these cucurbits in the cooler times of years. So when the weather was nice outside, cucumbers grown in containers could be grown out of doors, and they could get that natural sunshine. However, when the weather got poorer and was less conducive to growth, the cucumbers were moved inside the Specularibus. And it was really just a simple structure that had a mica, a thin sheet of a mica layer for a roof, or it had an oiled cloth, which would have just been a cotton cloth that would have been soaked in oil that was able to repel rain as well as hold in some heat while still letting light through to reach the plants. Moving on from the Specularibus, we started to get something called an orangery. And an orangery was a structure that was placed on the south sides of houses, and they had very large south-facing windows. This allowed light to come into the house during the low light winters, and it allowed crops like grapefruit, oranges, and figs to be grown in locations like the Netherlands, France, and England, where they might not otherwise grow outside. If you look at this slide, in the upper photo on the right-hand side, you can also see an image of a stove. And stoves were eventually placed into the orangery to increase the temperature a little bit more. And again, this started to be the prototype of our modern greenhouse. Once we saw the repeal of the glass tax in England, and France, and other parts of Western Europe, and we saw the development of rolled glass manufacturing occur, then we started to see the design of these Victorian conservatories. And these look very much like modern greenhouses, or much more so than the Specularibus that we already looked at. This allowed us to start to create large glass panes that were light enough to be suspended by the wrought iron infrastructure that was also developed around the same time here. Now, moving forward, we had the development of a high tunnel. And at first, this might look like a bit more rudimentary structure, but what was really interesting in the development of the high tunnel was the thin plastic film that was used at that covering. These thin plastic films are used widely in controlled environment production of cut flowers, whether we're talking about roses in South America or whether we're talking about lily crops forced in California in the field conditions. These thin films can be used to make temporary or low-cost greenhouse structures that protect plants from overhead precipitation like rain and snow, as well as trap some heat around them and protect them from cold temperatures, specifically at night. Now, this brings us to the modern greenhouse. And here we have a very good looking example of a modern greenhouse. And this is one that's in cut flowers. This is actually a cut chrysanthemum greenhouse. It's made out of glass. This is the Venlo style. So it's going to be that low profile, allows us to have small and short roof panels that don't require lots of struts and purlins. So you get lots of light transmission. We also have very high planting densities and minimal walkways. So again, this is a good idea of our modern greenhouse. But things are changing even more, and we're starting to see things like vertical farms being used. And so here we see an example of a modern vertical farm. This is going to be something that's used to produce leafy greens, specifically young short crop time things like microgreens. And let's not forget about space, the final frontier. It is also a controlled environment used for crop production. So here we have some images on some astronauts on the International Space Station. And on the left-hand image, they're harvesting arugula from NASA's Veggie Pillow, which is one of their systems that they use to grow plants hydroponically on space. But they're also growing zinnias, and you can see there on the right-hand side that cut flowers were the first floriculture crop grown in space. So this is a testament of the importance of flowers in our life, because yes, we do want to get good, nutritious, fresh nutrients and vitamins in the form of these leafy greens to our astronauts, but it also shows of the power of beauty and how that is important to people when they're on these long-term space flights. So now that we talked a little bit about controlled environments, let's talk a little bit more about hydroponics. So what is hydroponics? Well, let's look a little bit at the etymology of the word. First, hydro is, as you might think, water. And ponos means labor. So when we put them together, hydroponics literally translates to working water. When we often think about hydroponics, we think of this as a very futuristic sort of system. However, there are examples that this idea is much older than the 20th century when it was more formally created. So let's look at probably what could be the earliest example of a hydroponic production system. And that could be the Hanging Gardens of Babylon. Built around 600 BC in Babylonia or Mesopotamia, these gardens were built near the Euphrates rivers, and that Euphrates River served as the water source for these crops. And water was brought up in a chain and pull system. And a chain and pull system is very much like, for those of you who've seen the old Disney classic Swiss Family Robinson, they had the rope with the coconuts bringing that water up. That is essentially what a chain and pull system is, bringing water up from that Euphrates River to those hanging gardens. Another early example could be the Aztec gardens from South America. Now, what in these Aztec gardens, they were built in bodies of water, and some of the best examples were in Lake Titicaca. Sections were staked out in the lake, and a fence was created. Then inside of this fenced-off area, it was filled in with sediment, vegetation, and mud until it was above the level of the lake. Then these islands were planted, and they were highly productive, producing up to 7 crops throughout the year. They would get much of their mineral nutrients not only from the vegetation and the sediment that was packed into those islands, but also in the lake where they also got their water. And it ultimately would sub-irrigate, seeping into those islands and irrigating that crop. Now, the hydroponic ideas start to get a little more well-defined when the German scientists, Sachs and Knopp, were trying to determine which nutrients were essential for plant growth. This study actually formed the foundation for our modern-day understanding of plant nutrition in horticulture, not just floriculture. What they did was place plants in different water solutions containing different nutrient salts to identify what plants needed to complete their life. In each of the different nutrients, they created a deficiency of one specific element. So when they took away an element and a plant was able to still complete its life cycle, they knew that it wasn't essential for plant growth. But when they removed an element from that water solution and the plant was unable to complete its life cycle, then they could identify it as an essential mineral nutrient for plant growth. Really, the father of modern hydroponics would have to be William F. Garrick. He was a faculty member at the University of California, and he started to use these lab methods of hydroponic production to grow plants commercially. In fact, among those first commercial crops were vegetable plants like tomatoes, but also cut flower crops, including rose and carnation. So really, cut flowers were there for the birth of hydroponics. He also coined that term hydroponics, again, that working water, using those Greek root words. Now, his hydroponic systems, he wanted them to be used for commercial crop production. Those were his intentions. But really, the earliest adoption was by US troops who were in the Pacific in the 40s for World War II. And they were able to use these hydroponic methods to produce produce on islands that had little arable land, places that they couldn't get fresh produce to. And here we are today, and here's a picture of a modern hydroponic tomato greenhouse. We've got tomatoes that are grown in rock wool here, and this is really one of the more popular things that we're hearing about today. Again, controlled environment agriculture using hydroponic systems in greenhouses to grow food crops is a pretty popular part of our greenhouse industry now. But what goes around comes around. This really isn't new. So here we have an image of cucumbers. Now, admittedly, these aren't being grown hydroponically, they're being grown in a greenhouse. But does anyone by chance know where this greenhouse is and what greenhouse business it might be today? I'll give you a hint. It's up in Minnesota. This is the Bachman's family, and this is what the Bachmans were growing before they were producing greenhouse crops, greenhouse floriculture crops. They were growing food crops in controlled environments. So really, they made the transition from food into flowers. And that sort of ties all of this interest in controlled environment agriculture and hydroponic systems in food crops, as well as hydroponic flower production, sort of brings it all full circle. Now, I don't want to give you the idea that cut flowers grown in protected culture or in controlled environment agricultural systems are always grown hydroponically, because they're not. And so here we have two different examples. On the right-hand side, we've got a cut chrysanthemum greenhouse. And while they are in a controlled environment, that's a double twin wall polycarbonate structure, look down at the root zone. You can see that these crops are being grown in field soils. Those are not going to be soilless substrates. Those are going to be mineral soil derived field soils. Similarly, when you look at the image on the left-hand side, these lilies are being grown in field soils in California. We just have a protected structure over them. Again, keeping unwanted precipitation off the crop, minimizing damage to the flower parts, as well as providing some heat retention at night. But while not all cut flowers that are grown in greenhouses, they may not use hydroponic methods, many greenhouse cut flower operations are using some type of hydroponic crop production system. So let's think back to those different factors of plant growth, right? We had the 5 different factors. Well, our light, our temperature, and our carbon dioxide, those are going to be factors related to the greenhouse environment. Those are going to be factors that are relating to that controlled environment structure that we have. So let's not forget about those factors, but let's just put light and temperature and carbon dioxide to the side. We want to think about how we're going to provide water, nutrients, and oxygen in that water solution to our cut flower crops. And there are a number of ways that we can do that. And what I'm going to show you are some different examples of cut flower systems and how they actually are hydroponic, as well as some of the considerations that you'll need to have when trying to implement some of these systems. So here we have an example, and we've got some greenhouse grown cut flowers. These in this example, we've got some snapdragons. Now let's look down at that root zone. What do you see here? We have that native soil in the greenhouse has been taken out and it's been replaced with sand. Now, at first, you might say, is this really hydroponic crop production? But think back to the examples that we have of what really hydroponics is. It's just working water. It's soilless production. We are not using soil in this example. We are using non-mineral soil substrates. We're using inert sand. And you can see here that we've got drip tubes running down our crop, and we'll talk a little bit about that later when we talk about how water and nutrient solution is delivered to the plant. But that's going to be delivering that water with the fertilizer dissolved in it to the root zone of our crops on a frequent basis. This is essentially a hydroponic system, even though when you first look at it, you may think that it's more closely related to field cut flower production. But I would argue that it isn't, because we've got that inert non-mineral substrate. Here's another example. We've got greenhouse grown alstroemeria. Again, these are being grown in ground using air quotes. But let's take a little bit closer look at the root zone of these alstroemeria. So now, as we take a little bit closer look at this root zone in the alstroemeria, what do we see? Well, one familiar thing, we see that sand that we saw in that previous example. Again, all field soil had been removed from the root zone where these alstroemeria were going to be planted. But in combination with that sand, we've also got coarse perlite in this example, another inert substance, again, non-mineral field soils. So again, we've got these very free draining substrates. We've got that black irrigation tube running down that line of alstroemeria that's going to be providing the nutrient solution, the water, and the fertilizer to that crop several times throughout the day. Because there's not a lot of organic matter in this root zone, again, it's going to drain very freely, and this isn't going to be holding excess water. Because it doesn't hold so much water, it's going to be irrigating frequently, again, making this very, very similar to like those hydroponic tomatoes that I showed you in the previous slide. But we can culture plants in all sorts of different ways. So here we have a shorter term version of an alstroemeria crop. These rhizomes are just being grown, and this is an example where they're being grown outside, not inside a protected structure. But they're grown inside of a bulb crate that is going to be filled with peat moss adjusted with limestone. Something very, very similar to what we grow many of our bedding plants and flowering potted plants in, that standard peat and perlite substrate. Well, that works very well for these shorter term crops. Again, here's an example of lilies that are going to be planted in bulb crates. These organic substrates that you see in these bulb crates, I mentioned that they're more well suited to shorter term crops, and that's because over time, peat will start to degrade. Now, the alstroemeria that you saw grown in that perlite and sand mixture, that's a crop that's going to be grown for multiple years on end. If we grew that long-term alstroemeria crop in a substrate like a peat moss, the peat moss would degrade over that crop time. And as that peat moss degrades, it starts to shrink and you start to lose airspace. It'll hold too much water and not enough air. So how are we going to accommodate for those longer crops? Because some cut flowers can be really long-lived. And here we actually see an example of a rose rootstock. Although admittedly, you can tell this is not grown hydroponically, it can speak to the age of some of these crops. So again, we already saw sand used for alstroemeria, and as you could tell by some of the dead foliage in this cut flower system, here we've got a rose crop, and these again are being grown in containers filled with sand. By using sand as a substrate, it is physically and chemically inert, so it will take on the properties of the irrigation solution that you're going to be providing, but it's also not going to compress over time or degrade over time. It's going to maintain its physical structure and keep that airspace in the root zone for our crops. But there are organic options for longer term crops, and coconut coir is one of them. Coconut coir is made from the outer husk of coconut seeds, and it's going to be compressed into bales and then shipped into producers where they're going to be using it in their greenhouse. You can get coconut coir in a variety of different forms. It can be coarse chopped, it can be ground, and it can be shredded. Now, you might be thinking, why can you use coconut coir but not peat moss? They're both organic materials, aren't they? Yes, they are organic, little o, high carbon containing, not capital O, certified organic. They're both organic products, but coconut coir will not break down like peat moss will over the same amount of time because coconut coir has a very high lignin content. Because of that very high lignin content in coconut coir, the microbes that would be breaking down peat moss are not able to break down coconut coir. So it's got a much longer lifespan in the greenhouse because it will maintain its physical properties longer than peat moss. Rock wool slabs are another popular substrate to use for hydroponic cut flower crops that have a long production life. Again, in this example, we're looking at roses. And rock wool is pretty much thinking about it as geologic cotton candy. We're going to take a basalt rock. It's going to be heated to several thousand degrees, and then it's going to be spun into small fibers as it cools. Those fibers are then going to be packed together in different densities as well as orientations in a slab, and those slabs are going to be used for growing our crops. Again, this is chemically inert, so it will take on the properties of the nutrient solution that they're going to use. One thing you can do with rock wool slabs before planting is fill them with your floriculture nutrient solution for 24 hours and then let them drain. And then when you plant your crop into them, the pH and the EC will be adjusted to your nutrient solution. That's going to be a way that you can help get that rock wool ready for your plant to take off right after planting. You can use rock wool for more than one crop. So if you're using something, say a Gerbera daisy, and you want to reuse it for a subsequent crop, you are able to pasteurize it. So this is going to be very similar to what greenhouse growers used to do when we saw field soils being used for cut flower production for, say, carnations and roses in Colorado. You can cover your rock wool with a heavy canvas tarp, and then you can pipe steam under it to pasteurize it, raising the heat inside the rock wool for up to 30 minutes. And that's going to, it won't sterilize them, but will help pasteurize that substrate, reducing any potential pathogen loads that might infect your next crop. Now, while water culture is used commonly for growing hydroponic leafy greens such as lettuce and culinary herbs, water culture is not as commonly used for floriculture crops, but it is used for some cut flowers. Probably the best example of hydroponic water culture is going to be for forcing tulips. Now, forcing tulips in water culture is somewhat of a new method for the North American market. These tulips are received, then they're stuck onto trays that have solid bottoms that are going to hold that nutrient solution. You can see that in the upper left-hand image. When you place those tulips into these trays, in the bottom of the trays, there are little spikes, and you're going to press the tulip onto that, and that's going to help hold that tulip upright as it's developing. You can see those spikes in the upper right-hand image. Then the tulip is forced under those same air temperatures and lighting conditions that you would use for forcing any other cut or potted tulip inside of the greenhouse. You can see that crate developing in the lower left-hand image. And then when it comes time to harvest, simply go to the crates and pull the stem with the bulb out of the crate. Then as the stems are bunched, they're placed under a cutter, and that bulb and the root system is going to be severed. So how do we get our nutrient solution to our plants, that water and fertilizer? Well, with all cut flowers, we try to avoid overhead irrigation. That's because we don't want to add moisture onto our flowers because we don't want to damage them, nor do we want to get any sort of water on that foliage because there's a whole host of plant diseases that could reduce the marketability of that cut flower, chief among them, botrytis. So with cut flower production, we're trying to deliver that nutrient solution to the surface of our growing substrate or to the root zone. Now, you've already seen some drip tape in some of our examples, but here are some pictures more clearly showing its use in cut flower production. On the left-hand example, it's going to be drip tape that's laid down in a ground where, again, that field soil has been removed and it's been replaced by sand. On the right-hand image, we have a regular greenhouse with poured concrete floors, but instead, this is a carnation producer. They have built raised beds that they've filled with a combination of a little bit of field soil as well as soilless substrate components. And again, they're running that drip tape all down through that bed so it can deliver moisture below that cut flower canopy. Drip stakes, which are very commonly used in potted plant production, are also used, and here we have an example of drip stakes in cut gerberas. In this example, we've actually got gerberas planted into individual containers, and then they're grown in those containers for the life of the cut flower. But you'll notice that they are in a support that's used specifically for long-term production of cut flowers. And you'll see that in the next example. Why do we have 2 drippers per plant? Well, in some instances, you can really just think of it as insurance. When we're working with hydroponic systems, we're delivering a nutrient solution that's got salt dissolved in it. When that salt dries on our irrigation equipment, sometimes it can clog emitters. If we have a clogged emitter, we won't get nutrient solution delivered to our plant, and if that happens, we can have plant death. By using multiple drippers per plant, that can be an insurance policy just in case you ever do have a clogged emitter. So one of the hallmarks of many hydroponic systems is the ability to reduce your water use and your fertilizer use by capturing and reusing and recirculating your nutrient solution. So here we have a couple different examples of some of the systems you've already been introduced to. On the left-hand side, you can see that container system that is used for hydroponic cut flower production. We've got our pots filled with that coconut coir, and then we've got our drippers that deliver the nutrient solution. You'll notice underneath those containers are troughs. That's going to be where that leachate from the containers is going to be collected and run back where it's going to be treated and reused again on that crop. Below that, we see again our roses growing in a rock wool production system. If you look underneath that plastic, you can see some of those gutters that are running underneath the rose containers. And again, those gutters are going to collect the excess leachate from irrigation, and it's going to bring that water and fertilizer back into the centralized tank where it's going to be treated for reuse. So when we talk about treating our water for reuse in a hydroponic system, there are a couple things that we're going to be treating it for. One of the most important things is going to be the nutrient concentration. When we think about all of these different substrates that you've seen used in these hydroponic cut flower systems, they're not going to hold lots of nutrients in them. So again, we want to hold that in our nutrient solution. Therefore, when we bring our nutrient solution back, we measure the electrical conductivity, or the EC, which is the measurement of the total dissolved salts. Most of those salts are going to be, again, those fertilizer salts. If our nutrient solution is below our target EC, then a pneumatic pump will inject concentrated fertilizer or stock solution into our nutrient solution to raise the electrical conductivity until we see that target set point. We also are constantly adjusting the pH because we want to maintain good micronutrient availability. Generally speaking, we're injecting a type of acid, most commonly sulfuric, but it could be nitric or phosphoric acid. But we inject that acid to lower the pH, again, because we want to keep our micronutrients available to our crops. And as our pH drifts up, that's going to make those micronutrients less available, potentially risking a micronutrient deficiency, which is interveinal chlorosis, rendering our cut flowers unsaleable. Now, although we're recirculating our nutrient solution and maintaining our EC at a target level, it doesn't mean that the same nutrients are always available to our crops. So here is a little bit of data looking at our macronutrient concentrations of nitrogen, phosphorus, and potassium. And we've got our values at the beginning of a hydroponic experiment. We've got 247 parts per million nitrogen, 95 parts per million phosphorus, and 190 parts per million of potassium. Now for the next 3 weeks, every day the pH in the EC was adjusted to maintain a target EC of 2.0 and a target EC of 2.0 and a target pH of 5.8. Now, even though we were maintaining consistent EC and a consistent pH, you can still see that at the end of that 3-week period, we've actually got changes in the composition of our nutrient solution. We're adding the same fertilizer and the same acid every time, but plants aren't taking up all nutrients at the same rate. We also were using potassium hydroxide. That was allowing some potassium to be released into our nutrient solution. So after 3 weeks, even though we're still at that same EC we started at, you can see our nitrogen concentration is 41 parts per million lower. Our phosphorus concentration dropped by 24 parts per million, and our potassium concentration increased by 35 parts per million. So one of the most essential things for managing nutrient solutions for hydroponic cut flowers when you have recapturing and recirculating solutions is periodic testing of nutrient concentrations. We do a great job maintaining consistent electrical conductivities, but that doesn't always mean the concentration of salts is going to be the same ratio or that same composition. So you make sure you are always doing periodic testing to watch the buildup of different ions and maybe the depletion of other ions. When you start to get those imbalances, then we can drain part of our nutrient reservoir and bring in some fresh nutrient solution that is going to have our nutrients more in that balance that we want to have them. So we talked about water and we talked about nutrients. The other thing that we all wanted to talk about when we think about those 5 factors are gases. But remember what I said about gases? We're concerned about CO2 for leaves for photosynthesis. Oxygen, we're going to need to be concerned about those plants that are in water culture. So going back to those tulips growing in water culture, most any plant is amenable to growing in water. What makes a plant not tolerant of growing in water is usually not the water itself, but the dissolved oxygen concentration in that water. So here we have 2 different tulips. The tulips on the left were grown in a scenario where the water solution was adequately aerated and oxygenated, and you can see we have good healthy root growth. On the right-hand side, you can see a tulip that was grown in a system where the nutrient solution was not aerated and was not oxygenated. As a result, the dissolved oxygen concentrations started to drop below those target levels that we're trying to keep for plant culture to remain healthy, and we got stunted root growth, which was also going to result in a shorter stem and a poor quality flower, both of which are going to reduce the value of your crop. So when we think about all this put together, again, hydroponics is very popular right now. And it is a newer form of agriculture, and it's starting to get very refined. But when we think about it, the idea has really been around for several thousands of years. Maybe not in the same version it is now, but in a prototype form. Different types of hydroponic system, as well as elements of hydroponic culture, are commonly used for cut flowers grown in North American greenhouses, as well as protected structures outside of North America. Now, when we're thinking about how to grow hydroponic cut flowers, many of the fundamentals of plant production are going to be the same as traditional greenhouse crop production. The big difference is going to be thinking about how recirculating and recycled nutrient solutions are managed to maintain crop productivity. And floriculturists can capitalize on the new wave of controlled environment and hydroponic research, even though much of it is focused on edible food crops and not ornamental flower crops. Fundamental plant physiology doesn't change. And so we can look to some of the new advances that are occurring in the food crop sector, and we can look for new ideas of how we can better improve our hydroponic and controlled environment cut flower crop production. So, even though it is coming to the end of my time, I want to go ahead and remind you that we're going to be having another webinar in the Grow Pro webinar series that AFE is putting on sustainable disease management solution for cut flower growers. That's going to be on Tuesday, October 24th at 1 p.m. Eastern Standard Time. And that'll be presented by Dr. Francesca Han from The Ohio State University. If you're interested in registering for that, please go ahead and follow the link below, endowment.org/GrowPro. I really thank you for taking the time out of your day to learn a little bit about hydroponic cut flower production. And with that, I'd like to turn it over to you all to see if you have any questions that I could answer.
Thank you very much, Dr. Currey, for a wonderful presentation. And it was very interesting, and I can see that we already have some questions in the Q&A feature. So let me start with that. So Mary,
I can see them. So
right.
We've got Maurice Clark's, how is the leachate collected on sand or perlite systems? That can be hard. You're basically going to have some sort of a subsurface tile if you're going to be recirculating and recapturing. And I could have added a whole nother segment on open versus closed hydroponic systems, because I think that all of us tend to assume hydroponic systems are closed, meaning that the leachate is going to be recycled and recirculated. That's not always the case. So there can be systems that are open or drained away systems. But in these systems, we would have to try to put in some sort of tiling, like a drain tile in that substrate. The second question, what's the adequate level of dissolved oxygen in the water? Well, usually if we're using one of the more substrate-based systems like growing in sand or coconut coir, then we're usually not going to be inundating the root zone with water, and we can usually get adequate air just by having the airspace in the substrate. Now, if we were talking something else like a 100% water culture system, like a nutrient film technique system, or even more so a deep flow technique system, those systems, especially deep flow where you're pretty much in 100% water, there you're going to want to try and get close to saturation, around 8 parts per million. Saturated oxygen, the actual concentration will vary based on the temperature of the water, but somewhere around 7 to 9 parts per million, or like I say, usually around 8. That's usually a good concentration that we're looking for. So the next question, is nanobubble oxygen supply to roots useful? That can be an effective way to aerate your water to increase the oxygen concentration, but there are many different ways of doing it. You can use aerators to try and agitate the solution and incorporate that air that's got oxygen. You can also inject oxygen gas into your water. But again, that's not going to be something that you need to do unless you're in 100% water culture, which for the most part, we're not. So let's see, Donald, are there standardized nutrient solution guidelines based on real world growth? There usually are going to be published EC values that you can find. For roses, I believe that's Sonneveld, and who's the other co-author? I'm not trying to look away from you in the audience, but I'm looking at my bookshelf behind me. One of my grad students still has the book. Sonneveld and Vogt, Voogt. Sonneveld, Sonneveld, and then Vogt, Voogt. They have a number of hydroponic recipes that they've got in there. Most of them are going to be for food crops because, like I've alluded to throughout this presentation, that's the most popular. But rose is going to be another one. But it also looks like you're growing containerized plants, so that you might want to send me an email just to follow up with that. What
we have
is?
another. Go ahead.
I see a question from Pablo. What is the max sodium concentration and millimolar equivalents you can recommend? I can't give you a specific example, so I apologize for that, Pablo.
So I see in the chat also, Mohamed asked a question related with the nutrient recipe for growth and flowering stage for roses, which I think may be related to the book that.
Yeah, that should have. I believe the Sonneveld and Voot has a rose recipe in there. And then Robert, do you usually sanitize the reused water, or can you use without disinfecting? Anytime you're using any sort of recirculating culture, it's always a good idea to try and do some sort of disinfestation, whether that's through chemical treatment or whether that's through ozone or UV or something. Because as we're recirculating things, we can pick up undesirable things like maybe a root pathogen like Pythium. And if those get into these recirculating systems, which again is usually pretty popular for a hydroponic system design, you want to try and minimize the spread of those diseases. And so you talk about disinfecting them all the time, and that'd be sort of a continual or maintenance treatment, or periodically, and that would be kind of a shock treatment. And the best approach is to try and do it continually, because then you're always trying to always keep below that critical threshold. So you might not ever eliminate them entirely from your system, but you're continually treating to keep them below a threshold that would cause economic damage to your crop or your business.
Awesome. Let's see if somebody else is here. No, yet. I have another question here that it may be related to what you discussed at some point between like soilless versus control environment, but how different is hydroponic culture from regular substrate culture?
Yeah, well, I guess it kind of goes back to what you're saying about it depends on what you think hydroponics is, because I could make a pretty convincing argument that based on not using mineral soils, poinsettias grown in a 6-inch pot with peat and perlite could be hydroponic because it is non-mineral soil substrate. It's that organic medium or organic peat with perlite. And so in a way that could be considered hydroponic. So it's a bit of an evasive response, but it just depends on what you think hydroponic is. You know, some people, like I said, in Europe, some folks will consider tomatoes grown in rock wool substrate culture, not hydroponic. They tend to consider hydroponic pure water culture. I don't adopt that same mentality. I use soilless, mineral field soilless as basically a definition.
Awesome.
Yeah. Any other questions?
Let's see. I see another one in the Q&A. It's from Donald again. And it's basically to provide your email address to follow up with more questions.
Yes, Donald, it is CCURREY@iastate.edu. And if you forget that, you can go to the Department of Horticulture website for Iowa State University, and I'm the only faculty member with a substantial beard.
All right.
Any other questions?
Are other floriculture crops grown hydroponically other than the ones that you mentioned?
Well, like I said, it kind of depends. If you consider poinsettias and bedding plants, you know, if you consider peat and perlite soilless, then you could call those hydroponics. I think another example is I'm seeing some growers growing more edible flowers hydroponically. I think that the deep flow systems and the nutrient film technique systems are very well suited for growing edible flowers like marigolds or violas or nasturtiums and stuff like that. And often they're being put in a small clamshell, just like the herbs are. And so it can actually be a nice complement to a culinary herb, fresh cut hydroponic culinary herb program, because they're often packaged in the same way and put in the same part of the produce section.
I have seen those quite often, yeah. All right. I don't see any more questions. I'm going to give them a couple more seconds, but I think if no more questions are there, I would like to thank you all again for joining us today for another wonderful session of the AFE's Grow Pro webinar series. Please join us on October 24th at 1 p.m. Eastern Time for our next session on sustainable disease management solutions for cut flower growers. So please visit endowment.org/growpro to see our full list of upcoming sessions. Also, past webinar recordings, other grower-related resources, and research reports are available on the website. And they are free thanks to the industry support. We also want to ask you to please complete the brief survey about today's session, where you can suggest additional topics and help us to continue improving these webinars. Thank you all again for joining us. Have a wonderful evening.